Welcome to Train Signal. You're watching a video about network topologies. In this video, we're going to start off by taking a look at exactly what the word topology means. Then we're going to go in and look at some of our physical network topologies that we have available to us. We'll look at WAN technologies, which help to take our local network and turn it into a network that can span multiple cities or possibly even multiple countries. Then we'll take a look at what a VPN is, and then we'll look at what a VLAN is. So first of all, what does topology mean? Well, a network topology is the layout of the network. Now, a topology can be physical or can be logical. And here on the screen I have some drawings of some of the physical topologies that we're going to go over in just a moment. But beyond the physical layouts of our network, we also have logical layouts. Now, we spoke about some of these logical layouts in a previous video where we talked about the concept of having a peer-to-peer type network or a client-server network. That would be an example of a logical topology. Along those same lines, later on in this video, we'll talk about VPNs and VLANs, which again get more into the logical side of our network topology. So, taking a look at the physical network topologies. The first one I want to talk to you about is called the bus. Now, in the bus topology, all of the computers are connected in a straight line on a single cable segment. And I have that illustrated for you down here at the bottom of the screen. Okay, here we have 5 computers and they're all connected to one cable segment. Now, one thing you need to know about the bus topology is terminators must be used at each end of the cable segment. So here I'm just kind of drawing in some terminators. And the reason why we have to have these terminators is to prevent signal bounce. Okay, what happens is when a computer sends out a transmission out onto the cable, that transmission travels in both directions along the cable. And Electrical Engineering 101, when an electrical signal gets to the end of a cable, you know what it does? It turns around and bounces back. And it just keeps bouncing back and forth until eventually the signal deteriorates. And we learned, of course, that deterioration in the last video. We learned that that's called attenuation. But anyway, in this particular instance, we need for that signal not to bounce, because if it does bounce back, well, it's going to, signals are just going to keep bouncing back and forth on the cable, and then we're going to have a problem because signals are going to be bouncing into each other, colliding, and we have all kinds of troubles. Now, another thing you need to know about the bus topology is that if you were to have a single break in the cable, so if we were just kind of break this cable, it will actually take down the entire network. Now, it doesn't look like it, does it? I mean, it looks like these 2 computers can still communicate, and it looks like these 3 would still be able to communicate. But there's a problem. And the problem is that if we broke the cable here, we now have a cable end. Matter of fact, we have a cable end on this side and a cable end on this side of the break that's not terminated. So signals will be bouncing, and therefore communication will just stop. So, real quick review. Bus topology, computers all connected on a single cable segment. Terminators must be used at the end of the cable to prevent signals from bouncing back and forth and back and forth. And a single break in the cable will take down the entire network. Next, let's take a look at the star topology. In the star topology, all of the computers are connected through a central connection point so as to basically form what looks like a star, as you can see from this diagram right down here. Now, this central connection point, although it doesn't have to be, it typically is referred to, there's a device there called a hub. And the hub is responsible for taking communication that comes in and retransmitting it out to all other connections. Now, one big difference between the star topology and the bus topology is a single break in a cable. So if this cable were to have a break in it right here, it would only take down communications with the one computer. The remaining computers, the remaining network, would still be able to communicate. But if we were to have a hub failure, okay, so if the hub goes away, well then guess what? The entire network is now gone. because if that central point where they're all connected to goes away, well, I don't know how they're going to communicate. Next, we have the ring topology. Now, in the ring topology, all the computers are connected in a circular fashion, as we have down here. And data is passed around the ring. So basically, computers will pass data around the ring in one direction, from one to the other. Just keep going around the ring from computer to computer. Now, because of this, a single break in the cable, so if we break our cable, well, that's going to take down the entire network. Why? Well, because again, data is trying to travel around and round and round, and when it gets to here, it's going to say, oh, I'm done. So the entire network will be down. Now, in the last video, I mentioned something called a token ring network. And I will tell you that a token ring network is the most common form of network that uses the ring topology. But guess what? It actually uses somewhat of a physical star topology while working logically in a ring-like fashion. So what I have drawn here is I have a hub, and actually it's not even called a hub, it's called a multi-station access unit, or a MAU. And all the computers are connected into that MAU so as to form what looks like a star. But see, the red dashed lines that I have here are how data actually travels. See, what happens is when this computer sends it in, this is really nothing more than a wiring box who will send it back out to the next computer. Who will send it in, who will send it out to the next computer. Sends it in and back out, in and back out, and so on and so forth. So what ends up happening is it's as though the data is traveling around the circle in a ring fashion. The nice feature about this, though, is even though it's a ring topology, because it's physically a star topology, a single break in the cable does not necessarily take down the ring. Now, it depends on the equipment that you're using, but basically what happens in most of today's technology is this port will automatically know that there's been a loss of communication, and then the ring will just continue between the remaining 3 computers. It'll just go round and round like this until the one computer comes back. So that's the ring topology, which is, it's kind of interesting because we talked about physical topologies and logical topologies, and in this case the ring can be a physical ring. I mean, it is possible to actually wire the computers in a physical ring, but more often than not it is done in the form of a logical ring using the physical star topology. Next, we have the mesh topology. In the mesh topology, all of the computers are connected to all other computers. Well, but not really or not necessarily. First of all, it typically is used in a WAN environment. So maybe this picture would be better. Here we're taking a look at 5 different cities around the United States, each of which have an office, and then the offices are each connected to each other. So it's not so much that all the computers have a connection to all other computers, it's that each office has connectivity to each other office. Now, the second thing I can tell you about the mesh topology, it is not a requirement to have all computers connected to all other computers, or even all offices connected to all other offices. So as a for instance, in this example, maybe this connection doesn't actually exist. Well, it would still be a mesh topology. Okay, mesh topology just meaning that there is fault tolerance built in, meaning there are multiple connections back and forth to each other. Okay, and the fault tolerance is, as a for instance, if this line were to go down, it doesn't mean that this city can't talk to this city. They can. They'll just go maybe through this city and go that way. Or maybe they'll go down and up this way. Or maybe down and over this way. There's many different ways for this to happen because we have multiple connections and therefore have built in the fault tolerance in case a line goes down. Alright, so those are the 4 main physical network topologies. Once you are familiar with those, the next thing you need to understand is that you can have different types of topologies working together to form a hybrid topology. The example I have here would be something called the star bus. And the reason why is because we have star topology for this local network and another one for this network and another one for this network. But each of those three networks are then connected on a single bus. So we have three stars all connected over a single bus topology. There is no magical rhyme or reason to the hybrid topologies. I mean, you need to understand the pros and cons of the bus, the star, the ring, and the mesh. And if you see that there's an area within your environment that could maybe utilize both, as we have drawn here, well, then you can go ahead and do so through a hybrid of these topologies. Now, another thing that I will mention is technically, let me go back a page here, I suppose we could argue that this mesh topology right here is a hybrid, right? It's not really a mesh. Look, each one of these offices looks like it has a bit of a bus topology going there. So this could be like a bus mesh, right? Each office has a bus, but then each from office to office is part of a mesh. And maybe not. I would say what's more typical these days is each office would be in more of a star topology. That's probably the most common topology used today. And then again, each office would be connected to each other in the form of a mesh, thereby giving you a star mesh or mesh star topology. All right, so now let's talk a little bit about WAN technologies. And I have to tell you, going into this, that most of this is going to be just a matter of definitions. Similar to the last video, where some of the telecommunication stuff you don't need to be the foremost expert on. You just need to be able to have a somewhat educated conversation. You just need to know that things exist. Well, it's kind of the same thing here when it comes to WAN technologies. If you are going to take your network and branch out to where you are connecting multiple offices together, well, many of these WAN technologies which can do that are going to be provided to you by a third party. So unless you plan on working for one of these third-party telecommunications companies who is providing these WAN technologies, you don't have to know every last little detail. So don't worry about confusing yourself with this. So the first thing I want to tell you before we get into the specific technologies themselves is a couple of terms here. One is circuit switching. Any technology that uses circuit switching means that a physical connection path is established between the source and the destination, or we'll even just say the two locations, typically through a series of circuits, thus the name circuit switching. But in a circuit switched network, all the data is basically taking the same path. It's kind of a dedicated path that's been created. Whereas packet switching is where the data is broken into packets. So you take a chunk of data, break it into a bunch of different packets, which will each then possibly take separate independent routes over to wherever their destination is, where they then get reassembled back into data. And packet switching is a way of getting increased throughput by being able to use multiple different channels of communication. So, what are some of these WAN technologies? Well, just to kind of start us off real easy, the first two I have here are POTS and PSTN, which are essentially the same thing. POTS is the plain old telephone service, and PSTN is the public switch telephone network. It means just that. It means using good old-fashioned analog phone lines and using a modem, an analog modem to go ahead and dial up and connect to other offices. That's one WAN technology, one that we don't see really used anymore, but one that still exists. Another one that we have is the T1 or E1, depending on what country you're in. Matter of fact, technically there's even a J1, but we're not going to get into that. But a T1 is a digital leased line consisting of 24 64K channels, providing a total transfer rate, if you just do the math, of 1.544 megabits per second of throughput. Now the E1 is the European version, which actually has 30 channels instead of 24, providing a little bit faster speeds up to just over 2 megabits per second. A T3 or an E3 line is the exact same thing in the sense that it's a digital leased line, but a T3 is basically 28 T1 lines or 672 channels as opposed to 24 channels, providing a transfer rate up to over 44 megabits per second. And an E3 again is the European version, which has 512 channels, providing a little over 34 megabits per second. Now these are dedicated leased lines that you would need to get from a telecommunications provider. Another option that we have, although somewhat out of date, is something called ISDN, Integrated Services Digital Network. Now, the main thing you need to know about ISDN is that there are two different flavors. There is basic rate ISDN, which uses two 64K B channels, which means you're going to get 128K of throughput on your data. And it also uses a 16K, what's called D channel or Delta channel, to transmit the control information about the transmission. And primary rate ISDN uses a total of 24 64K channels, 23 of them as B channels for data and one D channel for control information, but essentially giving the same throughput as a T1 line, right? Because a T1 line is 24 64K channels. Moving along, here is something that was mentioned in the last video, something called SONET, Synchronous Optical Network. And we'll also talk about OCX, or optical carrier levels. Now, again, I don't want to get too deep into this. It really will just confuse things, but SONET is a network technology designed to carry large volumes of traffic over relatively long distances via fiber optic cabling. Now, I will tell you, besides the fact that it's done over fiber and it's very fast over long distances and all that good stuff, it's also typically done in the form of a ring. You may have heard the term SONET ring, and it's actually a form of dual ring so that you can have fault tolerance and very high speed throughput. Now, the actual data rates of your SONET network are divided into your optical carrier levels. And at the bottom of the screen here, I have the different OC levels, where basically we have something called OC1, which is a little over 50 megabits per second, ranging all the way up to OC768. And I will tell you, that's not as high as it goes. It does go higher than that, but OC768 would be 40 gigabits per second. So you can see there are some pretty fast speeds involved with SONET. Now, the one thing that I will tell you that you don't really have to worry about memorizing a chart like this. Okay, and the reason why is because all you really have to do is take OC1. So if you just know that OC1 is 51.84 megabits per second, and you just multiply it by whatever number we're talking about. Like OC3 is just 51.84 times 3 to give you 155.52. Okay, so you don't have to memorize the whole chart. I just wanted you to understand that there are many different optical carrier levels involved with SONET networks. Now, another type of WAN technology, matter of fact, here we have a couple of WAN technologies which use packet switching. The first is something called frame relay. Frame relay is a WAN technology where all nodes in the WAN network, or that's kind of redundant, right? WAN network, because WAN is wide area network, are connected through what's called a packet switching cloud. Now, the main thing that I want you to know about this is that if you're going to get frame relay, what you do is you pay a base price to the carrier for what's called a committed information rate, or a CIR. Now, this is like a minimum rate of throughput. But beyond that, there may be more throughput available. There may be more bandwidth available. But what I can also tell you is besides the base price just to have a certain level of guaranteed bandwidth available, you then only pay for the bandwidth that is actually used beyond that small minimum base price. Okay, so you're basically just paying a base price to turn the network on. And actually I should clarify, not only are you turning it on, but that base price will vary depending on what the guaranteed fastest speed is. But you may not ever use that fastest speed. You may not, and it's not even so much the speed as much as the overall throughput. You may not use all of it. You may have a situation where most of the time, most times of the day, maybe even most days of the week, you need a very small amount of throughput. But then maybe, we'll even say, how about once a month, right? Month end or something. You get some kind of massive data that you've got to get from point A to point B. Well, what happens is for most of the month where you're only using a little bit of bandwidth, well, you only pay for a little bit of bandwidth. But when you need that huge chunk of bandwidth, you need massive throughput, it's available because you paid that base price to get it available. And when you use it, well, then you got to pay for it. Okay, it's sometimes known as bandwidth as needed. Now, another one that's somewhat similar is something called ATM. No, not automatic teller machine, not where you go to get money, but asynchronous transfer mode. This is an advanced packing switching network which uses fixed length packets. They're actually 53 bytes in length. Every single packet, no matter how big the data is, it's going to be divided into 53 byte packets, and it can provide data rates up to 622 megabits per second. And actually, it has been known to be double that. It's been known to be a little over a gigabit through compression. So ATM, the main thing I want you to remember is the two bullet points I have here. 53 byte fixed sized packets and data rates up to 622 megabits per second. Now, there's another technology that we have to talk about here, and it's something called MPLS, which stands for Multi-Protocol Label Switching. Now, this is an interesting technology because you'll notice here it's not an actual service or an actual technology like many of these others, but it's a technique. Okay, it's more of a process of how WAN communication can take place. And because of this, it can be known by many different names. In other words, different carriers are going to implement the MPLS technique, but then go ahead and assign it some other name, some other marketing related name, because MPLS is not an actual technology. Now, the primary concept that I want you to keep in mind about what this is, I mean, first of all, look at the name, multi-protocol label switching. Well, multi-protocol, again, it's because it's not one specific protocol, it's not one specific service, it's not one specific technology. It works over many different protocols, services, technologies. And then we have label. Well, that's the primary concept. It uses what's called labeling. Now, it's very difficult to explain exactly what is meant by labeling and how this benefits without having a good full understanding of routing, routers, routing tables, etc., etc. And we're going to get to all that later on in the course. But for right now, the general idea is, to keep in mind that typically when a piece of data or a packet of information gets to a router, the router needs to then analyze each one of those packets independently to figure out where it's supposed to go and how it's going to get there. Well, the idea behind labeling is that what we can do is when a packet first enters into a network, it can be assigned a label, which gives the router kind of a quick piece of information so that it can quickly know how to get that packet to its destination without having to do a thorough analysis. Okay, so really what it's doing is it's kind of streamlining the process of going through different routers within a network. Now, again, you're probably going, huh? What? And you're feeling kind of lost because we really haven't covered everything we need to cover in order to understand or fully understand what this MPLS is. So there's a couple things I want to tell you. One, we are going to cover everything you need to know throughout this course to be able to grasp the definition of MPLS. And then second is right down here, I have a URL to what I think is a pretty good site out on the internet. It's actually through networkworld.com, where they have given a thorough explanation, including complicated diagrams and everything, of how MPLS works. So I wouldn't recommend that you go to this website right now, but after you've completed the course, once you've listened to everything and you fully understand how routers work, how routing works, etc., how things like the OSI model work, then go read this article. It's a very well explained article. All right, now we get more into the kind of the internet connectivity stuff as opposed to making connections to different offices. And we'll talk about where this can come in handy for connecting different offices in just a few minutes. But here we have DSL, Digital Subscriber Line. You've probably heard of DSL. DSL is quite popular for many of the home users, but it's also used in offices. DSL provides high-speed internet connections using the standard copper telephone wires. Right? In other words, DSL, who provides this to you? The phone company, that's right. Well, DSL also comes in different flavors. There is ADSL, which is asymmetric digital subscriber line, which allows POTS, the plain old telephone service, and data to be transmitted simultaneously over the same lines. Now, one of the things that you should know about ADSL is that typically your download rate is faster than your upload rate. Okay, that's how it's designed, is to go ahead and give you more download throughput by reducing your upload throughput. SDSL stands for Symmetric Digital Subscriber Line, and it cannot share data transmission with POTS. Okay, so unlike asymmetric, this cannot share data. You actually need to have separate lines, one for data, one for the actual phone service. You also need special hardware for SDSL, and you will see that it's not that commonly used. Now, the last one we have here is something called VDSL. I love it. They put a V in there for very high speed DSL, basically. And I'll tell you, VDSL is something that is somewhat new, not necessarily heavily used yet, not very well known about, but basically it's a concept that it's a technology that allows access to the maximum bandwidth available on your standard copper phone lines, which would be anywhere from 13 to 55 megabits per second, which actually is quite fast relative to your typical ADSL, which is going to be closer to somewhere between 1 and 3 megabits per second. All right, moving along from there, talking about internet connectivity, we have cable modem, where we get a high-speed internet connection through your broadband cable connection, same way your cable TV comes in. You've got satellite internet connectivity, where again, high-speed internet connections using satellites. Typically, you'll find satellites are used when DSL and cable are not available. Okay, so if you're way out in some rural area that doesn't provide cable, doesn't have DSL, you're too far from a switch, well, satellite, as long as you have line of sight, be able to go up and see into space, well, then you're going to be able to go ahead and get connectivity that way. And then we have wireless, which, this is a borderline, almost not even literally a WAN technology. It kind of is, and we'll talk about it in just a moment when we talk about VPNs. But wireless is used primarily by your mobile users, either connecting through what's called Wi-Fi hotspots, which It's not necessarily technically wireless. I mean, yeah, maybe a user takes their laptop, it goes into a hotspot, and they have wireless connection to their network, but that network doesn't necessarily have wireless connectivity to the internet. Or through the cellular phone network, where you do have something closer to a wireless connection. So those are your WAN technologies. And I will tell you before we go any further, if you are feeling like, wait a minute, I still don't feel like I have this solid understanding of what all these are. It's like you just gave me basic definitions. Well, that's right. You don't. And that's okay. You just need to know the basic concepts of each of these WAN technologies so that you, as a network administrator, if you are tasked with the duty of connecting your network to some other network in a different location or to the internet, you will know some of the options that are available to you. And I will tell you that these options are always changing, and you're going to need to talk to a third-party telecommunications carrier about what they have to offer and how much things cost and what the throughput's actually going to be. And that's where you need to put your focuses when it comes to WAN technologies, is you need to look at the needs of your business and weigh that against the cost, and then be able to have an educated conversation with a telecommunications expert and make a decision on what technology to use. All right, now moving along with more of the logical topology side of things, we need to talk about VPNs. What is a VPN? Well, VPN stands for Virtual Private Network, and it means just that. It means that virtually somebody away from the office who's not at the local network can connect and virtually be part of that private network. VPNs allow your traveling users to connect back to your local network while they're not in the office. Users remotely connect to a VPN server, which you'll have to have in place at the office, over a standard internet connection. Now, because it's over a standard internet connection, that doesn't sound very secure, right? Matter of fact, here in the drawing, what we have our office network, right? And the office is connected to the internet. So an example of where VPNs are used might be for somebody who works from home or somebody who's traveling using their laptop, and maybe they're on one of those Wi-Fi internet connections. Well, that's what we mean by standard internet connections. But the problem is as you go through this internet cloud here, it's not very secure, is it? And how is this part of your private network? Well, VPN connections are secured by using what's called a tunneling protocol. So basically, a tunnel is created from wherever the local user is through the internet to your local network, thus making it virtually private. Now, in case you're confused about this whole concept of creating a tunnel, because a lot of people try to picture that. They go, what do you mean make a tunnel? There's an actual shielded tunnel through the World Wide Web, through the internet? What is that? No, the tunnel is created through encryption. And we will talk about VPN encryption protocols later on in this course. So the last thing we have here is the VLAN. VLAN stands for Virtual LAN, or Virtual Local Area Network, if you want to spell it all the way out. Now, there are two ways of looking at a VLAN, and this is something that actually makes it kind of confusing. One way of looking at it is you might have one physical segment, okay, so one physical chunk of computers, meaning they're all connected on one cable through one device, right? If it's like a star topology, they can all be connected through one device. And by the way, that device, in the case of a VLAN, instead of being a hub, it more typically would be called a switch. A switch, again, is something we will talk about in more detail later on. But you have the one physical segment divided logically into two or more logical segments. Okay, so even though they're all connected together physically, the cable makes them all so they could talk to each other. Logically, you can divide them into separate segments so they don't really know about each other. Now, the other way of looking at it is the exact opposite. where you can have multiple physical segments. Matter of fact, those multiple physical segments could be in different cities. You might have different offices, but you can logically make them act as though they are on the same segment or the same local area network. Now again, VLANs is something that we will talk about later on in the course. Pretty much when we talk about switches, that's when we'll talk about VLANs. But for right now, just the general idea, this is all part of your network topology. Your network topology may be something as simple as this, a local network with a star, bus, ring, whatever. But part of the logical aspect of your topology might include users who work at home or are out on the road, and they are connecting via a VPN, so they're part of your network topology. And then we have the VLAN, which is where we logically change the topology from the way it's physically put into place. All right, well, that's pretty much what I have for you right now on network topologies. So we talked about the bus, the star, the ring, and the mesh topologies. We took a look at taking multiple topologies, putting them together, and making them hybrid topologies. We took a look at some of our WAN technologies, and we saw a high-level overview of some of the ones that are available to you. And then we saw how to logically change our network topology through the use of VPNs and VLANs. All right, well, that's it for this video. I look forward to seeing you in the next one.